Thanks all for coming. So, as he said, I'm going to talk about WebRTC. It's a kind of topic which is near to what I do for a living. I do telecom and voice over IP related stuff. So basically, I'm what the WebRTC guys call legacy. The code that I'm going to show is on GitHub already available, and I'm going to go through it a little bit. That's where I put all my toy projects or my hobbies. Feel free to check them out. Now, before we dive deep, I want to know what you people know, so we adjust. So who knows what WebRTC is? Put your hands. Okay. Now, from those of you, have you ever used it for something? Some application, maybe as a user or as a developer? Okay, less. And internals, anyone? What it does internally to achieve whatever it does? Okay, so then you're going to learn something new, I think. So what is WebRTC? The executive summary is that it basically is web real-time communications. It's an API devised by W3C that allows browsers to have audio, video, chat, and peer-to-peer file sharing between them without any plugins. So that is sort of the plan. And in order to have this, there is an architecture similar to this. This would be the web API. So this is what W3C designs, and that's a JavaScript API. And this is your WebRTC engine, so a big pile of C++ somewhere in the browser. There are very few implementations of all this, namely two of them, WebRTC.org, which is sort of the canonical implementation by Google. Since it's called the same, it can cause a bit of confusion. So WebRTC is a standard, a project, a website, it's many things. That piece of code is state-of-the-art technology in audio and video pipelining. So it's estimated that the amount of money required to build that thing today would be about 60 million. Those people basically purchased a few companies, amongst them Gibbs, the company that did the Skype's echo canceller. So actually it's great code in there which you can borrow, Apache license, so very nice, no patents, no anything, and you can use in your own projects. However, even if it launched in 2012-ish, it's still tagged as experimental in Mozilla's website. It's kind of full of prefixes, and well, the state of WebRTC support is still a bit sad. So notably, there is these guys from the fruit company over at Cupertino that don't seem to care, and well, it's kind of a big pile of devices, right? So there's this joke going around that WebRTC really stands for, well, everyone restarted Chrome, because we are going into this works only in Chrome arena sometimes. So you need an adapter, basically, these days. You need an adapter because there are API inconsistencies, things are still in flux. Google is basically sort of driving a lot of the things, and then sometimes there is this sort of, oh, it works with the latest Chrome, but not with the previous, so you need to have something there. You may even need more than one adapter, as I'm gonna say right now. In my demo, I used IVC Ninja because it has the best name, and also because it's written by a friend. So, and it's generally very nice. That's your URL. Definitely check it out. One cool thing about ITC Ninja is that it integrates with the next adapter, which is the Temasys WebRTC plugin. This brings WebRTC support to Internet Explorer and Safari. So there is a pun somewhere there because we are not plugin free, but we can use a free plugin. However, it's free as in beer, not as in freedom, so not good. At any rate, these are the three WebRTC APIs I'm going to talk about, and demo or whatever, if it works, we'll use ITC Peer Connection. If any of you has a laptop in the audience, please, and you want to collaborate with me, have it ready by the end of the talk so you help me out, because I didn't bring a demo wingman with me. So, First API is get user media, execute the JavaScript and the callbacks, but that's what you have because we are in a browser environment. This API allows us to capture, or let's say, talk to the camera and the microphone in our computer. So you can build sort of photo booth style applications. This is one of them where you render yourself as sort of this lead AA style. And you can do all sorts of effects there. The meat of the APIs is ITC Peer Connection, which is the API that handles the media communication between two peers. It uses all this state-of-the-art technology I talked about because some of it wasn't actually invented before WebRTC. So it popularized some and some got invented. The way you communicate with this media engine is there is this protocol called JSEP, or the JavaScript Session Establishment Protocol, which is you can have some JavaScript objects and decide how your session is going to happen, right? Do you want video? Do you want audio? Please give me some magical blob that I need to send to the other side to establish things. And also, it takes care of the ICE agent's state machine. I'm going to elaborate on that in a bit. So this is basically how WebRTC communication happens. So the caller, let's say Alice, gets her local media, then builds an SDP offer. So WebRTC will give you a session description in the form of an SDP, that is session description protocol. Some big ASCII text thing describing what codecs you support, what both audio, video, and basically how the other party can communicate with you. You offer your own capabilities, like, hey, I can do this. Then Bob here receiving this offer will get his own local media, so his own capability, because I may offer you video, but if you don't have a webcam, then I won't be able to see you. So you get your own capability, you build an answer, and send it back to Alice. Now, both of them know what their capabilities are, then they need to exchange ICE candidates. At this phase, they do connectivity checks, and they find the media path. So if we're in a local LAN, we might be able to do it peer-to-peer, but if there's a NAT environment, we might need to go through an external relay to bypass the NAT. And after the ICE checks have been done, and both endpoints know where the media is going to be, then audio and video can flow. And here I'll do a short intermission to go into what ICE is. ICE is Interactive Connectivity Establishment. It's a protocol that allows endpoints to discover the media candidates. So let's say in this laptop, so what IP addresses can I use to receive media? Well, usually at least two. So the local IP address of this machine, and then I can guess my own public IP address and put it there as well, just in case it helps. Now, we can also use a turn server, which is a relay. So if I know that there will be a NAT, I could basically talk to a server on the outside and say, hey, allocate the mapping for me. So I punch a hole in the NAT out, and then I talk to the server, and the server, using that port, will send the data back to me. And one thing that WebRTC brought into ICE, which wasn't new, was trickling, or ICE trickling. So in regular ICE, which is this part over here, both participants gather the candidates, then build the SDP, then they send it, and the other party does the same, and it sends it. Now, this ICE gathering mechanism and the further connectivity checks is a procedure that takes a little bit of time. That means that the call setup time could increase a bit. However, in ICE trickling, the idea is that you send your sort of naked SDP, and then as you learn about your candidates, you send them along a bit later, and then the connectivity checks will be done incrementally. Now, I've talked about how we do media, right? So we said we have an SDP, but how do we put that SDP across so that the other party gets it and is able to make sense of it? Well, it's not actually mandated or specified, which is great, because it means we can choose anything we want. So we can choose SIP, Session Initiation Protocol, or XMPP, or what have you. So kind of the web has spoken, and it has settled in to each their own. Basically, each application, each web application uses a different signaling protocol these days. So you can find tons of libraries on like easy RTC, simple RTC, hello RTC, whatever. I'm gonna show you like a couple. So at this point, you might think, well, I have enough to build like an Skype alternative. I suggest you don't do that because it's boring and everyone is doing the same. So do something more creative. Like friend Tim Panton, he made a pet monitoring system. So you can not only see your pet, you can actually communicate with it. Because you see, it's bidirectional. So yopet.us. Third API in WebRTC is the data channel. And up till now, you might think, well, we could do this with Flash. And you kind of would be right, because we have been doing audio and video in the browser with Flash for many years. Now we will do it without plugin and better. But data channel, which is a message boundary-based way of transferring data peer-to-peer. This means that the browser talks to the browser. And this wasn't possible before without actually some server in between, because one browser could not establish a connection to another browser. But now, all sorts of creative applications are happening. There was a peer CDN, which was like a CDN, but all browsers interchanged the data between them. And this one, for example, ShareFest, is a file sharing application. So let's say that if you're on the same LAN, you actually would be able to exchange files with other peers without any need for any server relaying. You just need a web server to have your signaling go across from one browser to the other, and then the actual file go from browser to browser. And at this point, I'm going to introduce sort of the project I did to kind of showcase some of these things. Call Roulette. It does exactly what you think it does. Helps you contact strangers on the internet. And how do we do that, and why, or where does Python fit in this picture? Fits here. So in the browser, I haven't tried Python or those things because, well, JavaScript is the native thing to do, I guess. So in the browser, on this plane, we're going to use JavaScript because it is what it is. But then our application, how we communicate with all the endpoints, there we will use Python in our backend, basically like many web applications. We just need to decide on what we're going to do. So what protocol we're going to use. We said it's not specified, so we can either invent one or pick one. So I decided to invent something a bit. So the protocol is basically me sending some JSONs over a WebSocket connection. So over those JSONs, we'll send these session descriptions, and we'll manage in such a way that both parties in a communication have the other party's session description as candidates and all that stuff. And after that is done, the connection will be established, and there's no actual message to finish the conversation. We just close the WebSocket connection. The idea was to make something simple, to experiment and learn more from it. The initial version of this protocol was a pun on the SIG protocol, so I called it Zaal's imbecile protocol. It had 3 messages, like offer request, then the first peer would actually send an offer, which got relayed to the other peer, which replied with an answer, and then the answer got replayed back, and then there we go, bidirectional media, and we wait for the end. But basically, this one doesn't use trickleized. It uses sort of the old way of gather everything in the beginning and send it, and this, well, it kind of you need to adjust to this in JavaScript. So when you ask for a session description to the WebRTC API, it gives you the candidates as they come, not all of them at the same time. So you need to wait for them. You need to deal with this complexity in your JavaScript code. But more than that, because it's not that complex, it's not like the native thing to do. So the right thing to do is to use trickleize. So I did this for the first time. I gave this talk, which was at FOSDEM earlier this year. But then today, I did the Yo protocol, which is the second iteration, so that we can compare them. So it has also very simple messages. The Yo message, it requests an offer. the yo plus an offer, as well the offer, which we can forward, yo plus the answer, and then both endpoints will actually send yo candidate with candidates. And this uses trickle-eyes. So a quick look at the messages. This is an offer request, very complicated. This is an offer. So after you get the request, we'll send a new yo message with a JSON. So the SDP that we requested from the browser, which is a horrible big piece of text that we would need 20 slides. So we skip that. And a pipe. Then the recipient of the offer will create a yo answer method, which looks exactly like the offer. And then both of them will gather candidates, and we will just send them like this. This is the serialized RTC ICE candidate JavaScript object. So it makes it easier to work with in JavaScript. So this is very simple for a very good reason. idea is to experiment, and basically, the more complexity you add to the protocol, the weirder everything becomes. And I, as someone who works with SIP and other protocols on a daily basis, can tell you that something like this can make your at least initial experience and steps a lot easier. Also, in Yo, we enhanced this, and now we use trickle-eyes, so we're doing better than the version 1. So I want to build this, so we need to go shopping, shopping for a framework or something. So I wanted to play with, well, something sort of newish, since I liked asyncio. I wanted to use it, so I needed to find a good excuse, so this was one. Then I wanted WebSockets kind of out of the box, so I didn't need to do any glue thing. And funny enough, when I started preparing this talk, there wasn't anything that worked out of the box, but when I actually started to write the slides, then it showed up. AO HTTP has WebSocket support since version 014 or something like that. So now we're going to dive a little bit into the code and see well, some of the things that I ran into, we noticed, or I think they're worth mentioning for one reason or another. Code is there already in a repository called Call Roulette. You can go check it out there, or you can follow along. So this is basically how you create your application. Instantiate an object of type web.application. Here I'm using a high-level API of AO HTTP. So there's a lower level, but this is the higher level, kind of nice. So in this, we add our routes, we put our methods, get here, then our paths, and then our handlers. A handler is any callable, actually, any coroutine. So as a kind of, not the trick, but the thing I do, because sometimes you want to keep state and stuff, is I use mainly classes where I override under call. And that way I can keep stuff as instance variables. An example of that is this very simple handler for static files. You don't want to do this in production, but for development, it's very convenient that you can serve everything from whatever directory you happen to be. So I override under call, and then this is our coroutine, and what I store in the instance variables is a cache. So every file I'm serving, I'm storing in memory. Wasteful, yes, but again, this is a toy, so who cares? Now, this is our WebSocket Handler, which hides a little bit of the meat. So the important thing here is we have two participants, right? Because there's always like two. It's not like there are 20 queued up and you pair them. No, like one participant comes in, when the second one comes, they go in pairs, then the third one comes, fourth one comes, they go in another pair. So here what we do is when we receive an incoming connection, what we do is we wait for another one. So the way for us to wait for another one is we need to wait for two things. Either this waiter future gets completed, which is another connection came, or you close your browser because you got bored of waiting for anybody. So here we use the asyncio.wait, where we pass two futures, so either of them could be completed. So if the waiter didn't get completed, then it means that the connection got closed. So we kind of can bail out, and that's it. However, if the waiter got completed, it means that there was another connection that came in, so now they can happily start talking to each other. So we would start this task, run roulette, passing both connections, and then we will do all the setup between them. Now, if the waiter is not none, it basically means that there's another connection waiting. So we set ourselves as the other party by setting our result. And then once we're done, all we need to do is wait until the connection is closed. If you're not very familiar with asyncio, you have many resources online. I made some presentations as well. But basically, keep in your mind that what's happening here is that when the first connection comes in, we wait for the second one. And if that connection that is waiting gets bored, we just bail out and free all the resources. Another thing that I think is interesting to note here is I'm using this module I found called JSON models. I'm not sure if you know it. Anybody know it? Okay, I think I see a few hands. So it's an interesting module because it allows you to define these models, and then the way you work with JSON is like you can actually validate the data. So I don't like JSON because I need to manually index dictionaries and things like that. But with this thing, like you can parse incoming data and you get back an object where you can do attribute checks and stuff. So it makes it very easy to both generate the payload and parse the incoming payload so that it matches what you want to match. So this is actually the models I am using, the your payload, the candidate, JSON. It is what it is. So now let's look at the actual run roulette, or how this whole thing works. It's divided into a few slides. So all of it is inside this big-ass run roulette function. So the first thing I do here is define a couple of helper functions. I want to close both connections. Close is kind of a protected method, so actually coroutine, you can call it a couple of times and it's okay because it knows if it's already closed and then it doesn't do anything. And parse is basically, it gets the raw payload and it parses the JSON and then the actual JSON model so that it validates it and checks if it's the right thing. Now, as I said, the first thing we need to do is, once we have both peers, we need to request an offer from one of them. So we send the empty yo payload and we send it. And then we wait until on that peer until we get an answer, or we need a timeout, in which case we tear down everything. Here, error handling is of the simplified form. Fuck everything and start again. Now, once we get our offer, if it's correct, all we do is write it as is to the other peer. Just as it comes, we write it to the other side. Then the other side will build an answer, send it to us. That's why we wait. We read our data, we parse it, and we end up with an answer object of the payload, which we do the same. We send it to the other side. So at this point in time, both endpoints know about each other. The offerer knows, of course, his own offer, plus the answer that he just received. So now we enter the kind of the bigger chunk here, which is we wait until things end. So while we wait, a couple of things could happen. The connection could be closed by either side, in which case we need to tear down the connections because we said closing the WebSocket is what finishes everything. Or we could get candidates that they need to be exchanged. So that's what we do here. We start 2 reading tasks to read from both peers at the same time because we don't know who will be faster in sending the candidates. We can't do like before. Wait on one, send it to the other side, wait on the other. So we do it in concurrently, not in parallel. And here we process the task. This is probably one of the ugliest for loops I wrote, because this way of breaking from 2 nested loops is sort of mind twisting a bit. Some people don't like for else. I'm a big fan. So anyway, what can happen here if any task gets completed is you can either have no data. So when you read empty string from socket, it means connection got closed. Here it means the same. So we break. When we break from this socket, we wouldn't enter into the else, because else for a for loop is only executed when there is no break for those who are not very familiar with 4 else. So we would break again, and then we break from the outer while loop, and we're done. And then we can close the connection. However, if instead of getting nothing, we get a candidate, then what we would do is write it to the other peer. And I kind of did a trick there to know who sent where, what, was I created a task, and then once I get a task object, I just attach the other peer to it. And that way I know where I want to write if that task completes. So this is how code works. And now, if the network is nice to me and there's someone willing to do the demo with me, is there anyone with a laptop that wants to help me out? Okay. So let's see. I'm going to do mirroring. So do I even network? Yes. So my IP address is that one. Keep it in mind when you connect. So I'm going to start the application here. And I'm going to start Chrome here. So I have WebSocket support, WebRTC support. That thing tells me there in the corner. And I'm going to start the roulette. And then I have a problem. Why? Well, reasons. We're going to use Ibarra. Did I break something? Okay. Oh wait, no. So there's this thing that happens to Macs. When your webcam goes nuts, like it doesn't want to cooperate, there is this VDC assistant which doesn't assist you in anything. So you force quit it, and then you like reload, and suddenly your camera shows up. So the plan here is that, oh, there's already someone. Okay, cool. So it is the demo. If I would be the first one, I would see myself for a bit so that I put my hair right. Now I'm going to try to do it from Chrome because I want to show you something. So hopefully that was all that broke with in Chrome. Yes, I want everything. So I'm now waiting, and when somebody joins the roulette again, the video will switch to the remote video. Don't let me hear for long. Hey, there we go. So, hello everyone. So the audio and video here is going peer-to-peer. Please don't close it. So we're going to look at something. So the thing here is going peer-to-peer because I did add a stand server so we can guess our own public IP addresses, but I'm reasonably sure that this network won't allow us to actually have a direct mapping on the outside for us to work. I'm going to show you a little thing that Chrome has, which is the Chrome
very close now, by the way.
WebRTC internals. Yeah, I'm kind of blind, sorry. So here we can see tons of information about what's happening internally in the WebRTC engine. And we're interested in, for example, knowing the candidates we gather. So here we can see, well, we can see for a certain degree of seeing. So here we can see the candidates that get added. So we have this candidate over here, which is, for instance, hey, what do you know? An IPv6 candidate. We have another candidate, which is another IPv6 candidate. Let's see, we find, there we go. And this is our private IP address, IPv4 candidate. So in WebRTC internals in Chrome, you can see a lot of the stuff that goes on under the hoods and can help you troubleshoot things. Because getting this to work on the public internet requires sometimes that there is a turn server, and then people that are not really used to these NAT environments, because the web doesn't suffer from them like that, may be surprised by the fact that things work on your lab, but then don't work when you deploy it outside. And it works from his home, but not from her home. So what's going on? And it could be different NAT types. So watch out for that. So the thing worked, which I'm glad. And that's all I have for you today. So if you have any questions, feel free to ask now or reach out to me. That's my real website. I planned very poorly today, so I have to leave like super soon. But really, I try to answer every single email I get. So if you run into anything, anytime, reach out. Or no, I guess.
Maybe we have a few minutes if there's a quick question of someone.
There's one there.
IPv6 solve your standard sheet?
Well, so the fact that every device can be reachable from the public internet doesn't mean that it doesn't have any filtering. So, like, yes, you can guess your own IP address, IPv6 address, and that might be visible for everyone in the world if it's a public one, not a linked local one. However, that doesn't mean that you're accepting all the traffic. You may have a firewall that basically only enables traffic if you have gone out, not like traffic coming straight to your box. Like you wouldn't open all the ports in your system to anybody from the outside. So this is sort of the same. And a funny thing about this whole ICE procedure is that well, some developers that were not very familiar with the model behind it were, oh, but this is a very important security problem because now you can guess your own IP address. But no shit, Sherlock, that's how it works.
It's not very new.
No.
Also, thank you very much.
Thank you.
It's very enjoyable.
Thank you.
Talking